This time I'll be talking about machine translation one more time. I didn't get a chance to talk about evaluation of translation 2 times ago, so I'd like to start out with that because that's pretty important. And then we can talk about the data augmentation strategies. Is this a little bit bright, like, and hard to see for people? Yeah, okay. Did anything change? Yeah. Okay, cool. Great. So let me skip to the evaluation part since we're going to be catching up on that. So machine translation evaluation is a very important and difficult topic in doing machine translation research. And in fact, I think we've gotten to the point where almost evaluating how well we're doing is maybe as difficult as like actually doing the translation itself. And the reason for this is if we output a translation, there are many different correct translations, right? So if I say, like, we could have paraphrases where the output is, this is a dog, I see a dog, there is a dog here, other things like this. And all of those would be appropriate for, an equivalent sentence in another language. So the basic evaluation paradigm in machine translation, there's 2 different types. There's human evaluation or manual evaluation and automatic evaluation. And this is the basic evaluation paradigm for automatic evaluation, where basically what we do is we have a parallel test set where we have an input and an output in the language pair that we're interested in. We use a system to generate translations, and we compare the target translations with references. Before I talk a little bit more detail about that, I'd like to talk about kind of manual evaluation. And this is the gold standard of doing evaluation of translation systems, where basically we ask human evaluators to go in and check whether the answer is correct or not. And to give an example, we take in a source side sentence, we generate some outputs, and you can either evaluate by having a human evaluator look at the source and the output, or look at a reference and in the output. And the reference would be like the so-called correct translation. Looking at the source and the output only works if you're bilingual in both languages. And it's somewhat difficult to get bilingual speakers, or at least more expensive. However, given the quality of machine translation systems nowadays, very often you don't know if the output of a human translator, like your reference, is better than the machine translation system. So like very often if you hire a person to do evaluation, they might not try super hard. Like I mentioned before. So kind of the gold standard is to get somebody who knows the source and the target to do the evaluation. There's a number of different axes along which you can do evaluation. I just listed a couple of them here. One is adequacy, and adequacy is basically whether the meaning of the translation is conveyed properly. And in this case, this is the correct answer here. You would know this if you knew Japanese, which most people don't, but if you knew Japanese, you would know the first one is correct. So this is perfectly adequate. It conveys the target message. The middle one is conveys the target message, but is disfluent. So it would score high on an adequacy scale, but on a fluency scale, it would score low. The one over here is fluent, but not adequate. So basically it switched the subject and object for, order, so it would be wrong. One notable thing about fluency is you don't need to know the source language to evaluate fluency. All you need to know is the target language, because it only has to do with whether the output is fluent or not. You can also do pairwise evaluation, which just says which one of these is better. One of the good things about pairwise evaluation is it's very simple because you just ask a question, which do you like better? Which do you think is a better translation? The problem with it is it doesn't give you an absolute idea of how well you're doing. So if you have two really bad systems and say which is better, one might be better, but they're both really bad. If you have two really good systems and say which is better, one might be better, but they're both really good. So kind of absolute scales have that advantage. Another thing is just like you might get bad translators, you might get lazy evaluators. If you hire people on Mechanical Turk and they're not very motivated, for example. So you need to be careful about quality control as well. There's human evaluation shared tasks. So the most famous one is the Conference on Machine Translation Shared Tasks. So I can show you a little bit what this looks like. They basically have a whole bunch, oops. They have a whole bunch of tasks that you can participate in. Most of these are tasks for actual translation, but they also have evaluation tasks on metrics and quality estimation. So basically what you try to do here is you try to create a metric that has the highest correlation with human evaluation. And for quality estimation, what this is essentially evaluation without a gold standard reference. So you're just given the input and the output, and you want to guess how good the system output is. And this is harder, obviously, because you don't have an example of what a good translation looks like. But it's also very useful in practical situations where, like, let's say you're a machine translation company and you want to decide whether you need to get a human translator to go in and check the output and correct it or something like that. So if that's the case, if you can estimate very accurately whether the input and output are correct or not, then that would save you money, save you time, give you confidence in the results. There's also other leaderboards and stuff for other sequence models, but that's a little bit less important for this multilingual class. So there are other metrics like Blue Score. So Blue Score is very famous. If you've done any research on machine translation or even heard of it, you've probably encountered Blue. The exact details of how Blue is calculated are what you do is you take the precision of n-grams output by the system. So for example, if you look at the unigram precision, that's out of all the unigrams that the system output, how many of them exist in a reference or one of the references that you're provided, if in the case that you're using multiple references. And this gives you a precision of like 3 out of 5. And then you take the geometric mean of n-grams, usually 1 to 4. And then you also have a penalty for outputting 2 short sentences, because one way to improve your precision is to not output very many things. So this is basically to prevent you from gaming the system. But the important thing is not the details of how Blue is calculated. Probably the important thing is that this is a lexical metric, which means that you're just doing exact match with the references. And this has a few issues. One of the issues is essentially that so there's 2 major issues that cause Blue to either underestimate how good a translation is or overestimate how good a translation is. Blue tends to underestimate how good translations are when the translations are paraphrases of the true reference. So if you, for example, had, I went to the store and bought a book yesterday, and you compare that with yesterday I bought a book at the store. Those are almost identical in meaning, but they would get a low Blue score because I've just rearranged the phrases a little bit. So that's when Blue tends to underestimate scores. Blue tends to overestimate scores when you get very critical words in the sentence wrong, but get everything else right. So for example, could you please send this big package to Philadelphia? Turns into, could you please send this big package to Japan? That would get a very good blue score because most of the words are the same, but your package would go to Japan. And that's probably not what you intended by that utterance, right? So that's the downside of blue. It's basically not smart enough with respect to these. So recently, yeah. So the brevity penalty basically gives you a penalty if your output is shorter than the intended output. So if the reference is like 20 words and your sentence is 15 words, you would get a penalty of about 0.75. It's not exactly like just the ratio. It actually drops off faster and stuff like that, but that's a basic idea.
Is there any penalty that the translate sentence is much longer than before?
That's a really good question. So you pay a penalty in your precision. Your precision goes down by a lot because there's no way to get good precision if you output too many things. One thing you should know about blue, if you're using it in your research, which you might, is that it's very, very sensitive to the length. So if your length is a little bit too short or a little bit too long, it hurts your blue really badly. So that's another problem with blue, essentially, is that it's not sensitive to like paraphrases that are too long or too short as well. So recently, in the past 3 years or so, there's been a huge improvement in embedding-based metrics, which are basically metrics that take advantage of recent NLP techniques. And one of the first ones was Bert Score. And these can be separated into unsupervised metrics and supervised metrics. Unsupervised metrics require no annotated data of whether a translation is a good translation or a bad translation. Supervised metrics are trained to basically regress to an estimation of how good a translation is or not. So Bert Score is an unsupervised metric that's based essentially on the similarity between BERT embeddings. So it has this matching algorithm where you basically, for each word in the output, you try to find how good it matches with one of the words in the input. And this is good because it can do things like handle paraphrases as long as the paraphrases have similar BERT embeddings. Another famous one is BlueRT. And what they did essentially was they trained BERT to predict human evaluation scores. So they essentially solve a regression problem from the sentences, like the reference and the system output to an evaluation score. So they're just going and directly predicting evaluation. And they have a bunch of other tricks like unsupervised training where they try to predict blue or rouge or other lexical metrics beforehand, and that makes it more robust. The favorite one that we use in our research on MT now is Comet. And Comet is also similarly, it trains a model to predict human evaluation. But in addition to using the just the system output and reference, it also uses a source sentence, which means that it essentially, I talked about human evaluation, right? Where you can either ask a human evaluator to look only at the reference or also look at the source. And for a similar reason to why we would like a human speaker to do that, it's also useful to have the model do that because the model can look at the source and see if the information is reflected in the target. And the final one, Prism's another one based on paraphrasing. The final one is Bart Score, and Bart Score is one that I'm a co-author on. This is a unsupervised metric that is based on basically a generative model that tries to generate the system output using the reference, or the reference using the system output, or the source using the system output, et cetera, et cetera. And Bart Score, I think, is good because it's unsupervised like Bert Score, but it's essentially more accurate and more controllable. So you can do things like calculate recall, calculate precision, and other things like that. So if that sounds interesting, you can take a look at the paper as well. But basically, if you're doing MT, I would suggest using Comet now because it's well supported. It has a nice package. It's pretty widely tested, and follow-up reports have suggested that it has very good correlation with human evaluation. So that's my suggestion. You can trust me, but you don't necessarily need to trust me. So like, as I mentioned, meta evaluation, basically what it does is it runs human evaluation and automatic evaluation on the same outputs and calculates the correlation. This is what they do in the WMT shared tasks, like the WMT metrics task for MT, other things for summarization, etc. And one interesting thing is that evaluation, as I mentioned at the beginning, is pretty hard, especially with good systems. So most metrics actually had no correlation with human eval over a subset of the best systems at some of the WMT 2019 tasks, which means that basically all of the evaluation metrics we had were kind of broken on like evaluating really good MT systems. So fortunately, now we have Comet, we have other things like this that actually seem to be a lot more robust, but it was a major problem then. Is your hand?
So how do we determine when the system is doing better or worse?
So you basically calculate the correlation. You calculate Pearson's correlation or Spearman's correlation. And the way you do that is you do human eval of a whole bunch of sentences or human eval of a whole bunch of systems. And you try to find the metric that has the highest correlation between the evaluation scores of the systems and the evaluation scores given by the humans. Yeah, yeah.
I think an issue I've had with language-based methods is that they often don't support that many languages.
Right.
Do you have like any suggestions or workarounds for that?
Well, so that's a really good question. Many of them do use something like MBERT or XLMR, which support a lot of languages. XLMR actually, MBERT's a little bit more biased. XLMR has pretty good coverage of the most common languages in the world, but of course, as you go down to less well-resourced languages, that's going to continue to be a problem. There, you might be stuck with Blue for now, but honestly, if you have really bad systems, really bad MT systems, I still think Blue is probably good enough in many cases. Oh, another option is CHARF, CHRF, and that's a character-based evaluation metric for MT that's particularly good for languages with like rich morphology or something like that. So I think when you're working with low resource languages, your MT systems are also going to be really bad. So any metric you have is still going to be like reasonably good at measuring progress. So, cool. Yeah, so the next thing I'd like to talk about is the database strategies to low resource MT. There's not a whole lot of content here, so I'll try to go through it rather quickly to leave time for the discussion. But basically, we have data challenges in low resource MT. So MT of high resource languages with large parallel corpora gives us, very good translations. But low resource languages with small parallel corpora, if you just train there, you can end up with nonsense. So this is an example of a system trained on 5,000 languages. And the most frequent failure state is basically that a neural MT system will just spit out something that has nothing to do with the original input. There's a famous example of this. That says, why is Google Translate spitting out sinister religious prophecies? And basically, if you put in dog, 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 dog in Maori, it outputs doomsday clock is 3 minutes at 12. We are experiencing characters in a dramatic development in which Jesus returns. Can you guess why this happened? Yeah. Exactly. They use Bible data in training their system. And when you use Bible data in training your system, and your system doesn't know what to do because it has so few resources, or it sees something it doesn't know, it just reverts to using the language model. and basically outputs whatever the language model thinks and thinks it looks likely. And so, if your system is trained on Bible data, that looks like the Bible. If your system is trained on something else, it looks like something else. So, that's basically what happened here as well. So some ways to fix this. We can transfer from high resource languages to low resource languages. So basically what you do is you train on a high resource language or multiple high resource languages, and then you adapt to the low resource language. The simplest way to do that is just to continue fine tuning on the low resource language. You can also do joint training with the low resource language and the high resource language. So just concatenate all of the data together and train. So this is okay, but there are some problems with this as well. One problem is suboptimal lexical or syntactic sharing. And another problem is it's not possible to leverage monolingual data because you still require parallel data here. And I'm going to be talking more about like lexical overlap and loanwords and stuff in the next class. So I'll cover that more there. But basically, suffice to say, the high resource language and the low resource language are different. So training on different data is suboptimal for information sharing. So if we think about data augmentation is basically generating other data that looks like the data that you want to have. The very convenient thing about this is generating more training data and feeding it into your existing system is easy but effective in improving MT performance. So it's actually a pretty widely used technique now. So if we look at the available resources, we might have a low resource language parallel data, a high resource language parallel data, and also, for example, target data, which is monolingual, hence the M here. And what we do is we would like to create augmented data where we have target data and like pseudo low resource language data. And train our model on this, with the idea being that if we can create this, this will be closer to our final evaluation scenario where we want to generate the target given a low resource language. So the first example is back translation. And the way back translation works is basically we train a target to low resource language system. And we take our monolingual target data and we generate fake low resource language data by translating the target data into the low resource language data. So this is how it works. We take our target to low resource language system. We back translate using the system, and then we train a low resource language to target language system using the concatenation of this augmented data and the original data. And the key point here is that when we're training like a sequence model or a machine translation model, we're training it to do two things. We're training it to do language modeling on the target side only. And we're training it to do mapping between the source side and the target side. And in order to do language modeling, we only really need good target side data. So even if there's some degree of error in this like low resource language here, we'll still be able to learn target side data, and we'll be able to learn the language model from target side data, and we'll be able to learn a mapping, even if it's imperfect, from the low resource language to the target language. So there's a couple ways to generate translations when doing back translation. The first one is using beam search. Oh, sorry. Yeah.
Some sort of a training schedule that's being used when you combine the augmented data and the ground goal tool data. So do you first train on the goal samples and then you reduce the learning rate with the augmented one, or do you just have a balanced bag?
Yeah, that's a really good question. So the question was, is there any sort of training schedule that you use when you do this? So the kind of quote unquote obvious training schedule that you might do is you might train jointly on both of them at first and then fine tune on this data over here. And that would make sense because this is good data. This is like actually translated data. However, there's another issue, which actually is not super obvious at first, but it's maybe obvious in hindsight, which is that if this data is all from the Bible, and then you want to translate news, then actually fine-tuning on Bible data will be really out of domain and cause issues for you. In fact, in the original back translation paper, they threw away this data and only trained on this because it was more in domain, and that ended up giving better results. But that was predicated on the fact that they have a good, back translation system in the first place. So it's not necessarily clear what the ideal schedule is, but you would almost certainly benefit from some sort of schedule or balancing or something. But that's a complicated hyperparameter. So because it's a complicated hyperparameter, it's also very common to just concatenate the two and work with that. These are good details to know for assignment 2, by the way, because they might make a difference in your final scores. How to generate translations. So beam search is one way. And basically what this is doing is selecting the highest scoring output. This was done in the original paper. This has the advantage of having higher quality, but also lower diversity in the outputs and a potential for bias. So you might, for example, one result is beam search tends to mostly output pronouns from the majority gender because they're overrepresented. So you might only get male inflections if you do beam search. So that's a type of data bias that could result from here. And so the other option is sampling. And what you do is you randomly sample from the back translation model, which gives lower overall quality, but higher diversity. And most reports say this works better at the moment, sampling. And also we had a recent paper, which I'm going to introduce in a second, but this has kind of a theoretical explanation for why we think sampling should be better, which is that it's a better model of the underlying data distribution that we're trying to model. So I think I'm pretty firmly a believer that sampling is the way to go. Yeah. There's also a method of iterative back translation. This is particularly useful when you have large monolingual data in both languages. And again, the idea is simple. You train a low resource language to target system first. So this is going in the direction you originally want to translate. You generate pseudo data with the target language. You use that to train your target to low resource language system. You back translate, and then use this to train your final system. So this is, now you have 3 systems, your forward translation data augmentation system, your back translation data augmentation system, and your forward translation final system. You can do this as many times as you want, obviously. You could also do it on the fly in the process of training the system. So this can become arbitrarily complicated if you want. Just one example of this. This is a paper that I just talked about, but we have a paper called Metaback translation, which I think is kind of an interesting idea. So normally when we're training this system to train the low resource language to the target language system, we're backpropping the gradient from this low resource language data. But we can also do a back propagation step where we basically train, oh, sorry, that arrow is wrong. I apologize. So the arrow actually should be going from here around this to here. So the basic idea, I'll fix this later in the slides, but the basic idea is we use the signal that we get from training the final system that we want to train to update the parameters of the back translation system. So we're essentially training the ideal back translation system to train a good forward translation system. So this is I like the idea behind here, which is basically the final goal of the back translation system is to improve the forward translation system so we can directly optimize it to do this. So there are a couple of issues here. The first issue is that back translation often fails in low resource languages or domains. And as a solution, one thing that we can do is we can use other high resource languages, or we can combine them with monolingual data, maybe with denoising objectives, which we're covering in a following class. And we can perform other varieties of rule-based augmentation. So I'm going to go through these in a little bit, in maybe in a few minutes. So also, actually, we'll have discussion about these two. So maybe I'll just briefly explain the idea, and we can discuss more in the discussion for people who read those papers. So using high resource languages in augmentation, the problem is target to low resource language back translation might be very low quality. So the idea is we can also use a high resource language that's similar to the low resource language. And basically, for example, if we have something like Azerbaijani and Turkish are very highly related. So maybe we could use information from Azerbaijani to English translation, back translate into Turkish, which is certainly going to give us higher quality data, and use that to augment our data for an Azerbaijani English system. And then we can just throw away this Azerbaijani data that we know is not going to be very useful. So that would give us additional high resource language to target language data. And another thing we can do is we can augment via pivoting. And so basically what that does is that gives us data where we take the high resource language data and we translate that into the low resource language. And presumably translation from the high resource language to the low resource language is easier because these languages are more related. So basically what this does is that gives us better like low resource language pseudo data here. And we can also do a similar thing where we generate more high resource language data. And this basically gives us 3 different ways to create this pseudo parallel data between the low resource language and target language. Another simple trick, this is kind of like frustratingly effective at improving your models, is monolingual data copying. And the issue is that back translation may help with structure, but one of the issues with low resource language systems is that they tend to fail really badly on unusual vocabulary. So like, for example, proper names or something like this. So you might get a back translation system that's very good at getting the structure right, but gets all of your proper names and entities incorrect. So basically, one thing that you can do here is you just copy the target data into the source data, and then you're done. This kind of guarantees to maintain the entities, so or the rare words. So that will help mitigate these issues of like vocabulary being dropped. Yeah.
Something to point out with copying is that even in languages with different scripts, it seems to work really well. Maybe because of autoencoder objective.
Yeah, even in languages with different scripts. And there's actually a nice paper by the same authors who wrote this paper. Where they examine this, and basically the idea here is they are trying to figure out like what transfer learning, why does transfer learning have this positive effect? And basically, one of the things that they show is that even just making sure that the length is the same, is approximately the same, or making sure that the words are output in approximately the same order as the input is effective for improving translation accuracy. So if you have a low resource language, the translation system might drop half the content, or it might like totally mess up the order or something like this. So this paper is demonstrating that kind of just like a monotonic bias and a bias towards outputting approximately the same number of words gets you a long way in improving the results. Which of course monolingual data copying would also do. And so for the final things, which we're also reading, so we can talk more about them in the discussion, we had dictionary-based augmentation, and dictionary-based augmentation basically finds rare words in the source sentences. It could also be in the target sentence, and tries to replace the words with other words that are kind of in the same semantic class. So it replaces car with motorbike. And then using a lexicon, it replaces the words in the target sentence as well. So it's basically creating more sentences to augment the data with like words that are less frequent in the original corpus. And in order to do this, they need to use a tool called word alignment. And what word alignment does is it essentially takes in two parallel corpora. And the parallel corpora, you want to find which words align to each other in the source and target sentences. And this is useful for a number of reasons. It's useful for analysis. It's useful for cross-lingual transfer learning. I talked about supervised alignment as a training method last time, I believe. And there's a couple methods to do so. There's, again, traditional symbolic methods, which, like BLUE, are based on exact lexical match or some variety of clustering. Giza++ has some clustering involved in it. But recently, neural methods have been largely outperforming these. And I can recommend highly our aligner called Awesome Align. I didn't name it. I'm far too humble to name my aligner Awesome Align, but it's pretty awesome, I have to say. And basically, it uses multilingual BERT, and it tries to find things that are similar, but it's also fine-tuned multilingually on supervised data. So basically, there's some supervision that goes into it to try to inform the aligner about the outputs. And it works on any language that's included in MBERT. Again, like the question before, it won't work on very low resource languages, of course. So then you might be stuck with Giza++ or FastAlign. You can also do things like word-by-word data augmentation, where you simply translate sentences word by word into the target sentence using a dictionary. This is another frustratingly, effective method like monolingual data copying. However, there are problems like word order and syntactic divergence. So if you get like the new car bought, number one, the order is strange. Number two, these words don't actually align with each other. So that's a problem. Other things you can do are you can try to decrease this divergence with reordering or rules. So this was also another paper in the potential reading. And basically what the idea is that you a priori do some reordering from one language, from English into like reordered English, and then do data augmentation on top of that. And the good thing about this is like English has a lot of analysis tools. You could like do syntactic parsing of English, get the syntactic structure, build reordering rules on top of that, and then just apply dictionary-based translation. And then the hope would be that you would get something that looks a lot more like Japanese than if you just translated English word by word. And one interesting thing we showed here was we demonstrated that this was useful for Japanese translation, but then we applied the exact same reordering rules and also applied it to Uyghur, which is another language that's completely different language family, but it has very similar syntax to Japanese. So because of that, the exact same reordering rules for English were still effective in improving the results for Uyghur to English translations. So because of that, it's not language dependent, it's rather syntax dependent, and because there's syntactic similarities between the languages, it helps. So yeah, given that we now have the assignment, actually this slide is missing one of the papers that was a potential paper to read. So first, before we go to the discussion, are there any questions? So I kind of breezed through it, the last part quickly, but hopefully we can also talk about them in the discussion. Okay, if not, this time we're going to try a new experiment. We're going to try to make 6 groups. So the groups are going to be half the size, and they're going to be front, middle, front right, front left, back middle, back left, back middle, and back right. So we're going to ask everybody to talk a little bit more quietly, but also you'll be in a smaller circle, so hopefully that'll be easier. And yeah, let's go ahead. And actually, guys, since we're running a little bit late, I think maybe we'll skip the reporting part this time. Is that okay? And we'll just, be within our groups. And if there's anything really interesting, we can share on Piazza or something. Send it. Okay.